Hi, I'm Brian Blanca. I'm a VP at an engineering firm.
Hi, I'm Dylan Hull, and I am an electrical engineering student.
Hi, my name is Robert McVicker, and I'm an electrical engineering student at ASU.
Hello, my name is Justin Ramsey, and I'm an ASU student majoring in electrical engineering.
Hello, my name is David Sigdestad, and I'm an electrical engineering student at ASU with a concentration in electrical power and energy systems.
Despite nuclear energy being a major source of clean power, students and trainees rarely get to explore how these reactors actually behave. What happens when you pull a control rod? How does the system respond when the grid needs more power? Understanding these dynamics is essential, but today's learning tools miss the mark. Professional simulators overwhelm newcomers with complexity built for trained operators. Introductory tools show static parts, but not the physics. What's needed is something different. A simulator that shows real reactor physics in action, but keeps it accessible, where you can move a control rod and watch power levels respond. Change the load and see temperature, pressure, and power respond together across the system. Because whether you're a student or an expert, there's no substitute for seeing a system come alive.
Our project focuses on creating a computer-based simulator of the AP1000 reactor, modeled as a multi-loop pressurized water reactor. It captures the behavior of the primary system, things like the core, the hot and cold legs, the pressurizer, and the U-tube steam generator, while leaving out the turbine and feed water systems so we can focus on the reactor side. The simulator is built in Python for portability and uses analytical models such as point kinetics to represent time-dependent behavior. Users interact through a simple game-like interface that lets them adjust control rods and load demand while seeing real-time plots and visuals of how the system responds. The end goal is a technically accurate but accessible tool for nuclear education.
Now we've specified the scope of our project, I'm going to talk about why it matters to you. Since 1957, the US has utilized some amount of nuclear power production. 2023, almost 10% of the power that we consumed was from a nuclear plant. Reactors aren't built overnight. They require extensive testing and significant design for safety and other features. The designers need a way to test the reactors, and the operators need a way to train on models. We're trying to make these concepts more approachable by the designers and to make the concepts more approachable to the general public.
Success for this project is defined by developing an interactive simulation that models and simplifies key AP1000 reactor concepts. The simulator will highlight how operator actions such as adjusting control rods or changing load affect overall reactor performance and system balance. The simulation benefits multiple audiences. Nuclear engineering students gain a clearer understanding of reactor behavior beyond theoretical studies. Professors can use it as a tool to illustrate reactor dynamics in real time, while industry professionals apply it for continued learning and skill development in the workplace.
Building a simulator of a real nuclear reactor brings some big challenges. The first is showing how the system really works without overwhelming users. We're focusing only on the main parts, where the heat is produced and moved. This keeps the simulator clear while still showing the real physics behind it. The second challenge is turning that science into working code. We're taking a bottom-up approach, building and testing the smaller pieces first, and then connecting them into the full system. That helps us spot and fix issues early. And finally, we're designing an interface that's easy and fun to use. We're creating prototypes, testing them, and improving them based on what feels the most natural. Our project is built on collaboration and communication. Everyone takes part in research, coding, and design, while weekly meetings keep us organized and give us a chance to share feedback. The work follows a clear timeline. We began with research and design in September, moved into coding and testing through December, and then we'll finish with the interface and documentation from January to May. In the end, PWR play is about making nuclear power education easier to understand and more engaging. By combining accurate physics with an interactive design, we're helping students connect theory to the real behavior of power plants. It's a bridge between the classroom and the clean energy world ahead.